Okay, good morning. Let's get started. So we were talking about centripetal force. Centripetal force is the force that keeps an object in circular motion. So one of the most universal centripetal force that is common everywhere in the universe is gravitational force. Okay, so if you think about the motion of Earth around the sun, so Earth tends to move in straight path, but sun pulls the Earth towards its center, and because of that Earth moves in circular orbit. Okay, so at each and every point along its orbit, Earth tends to move straight, but because of this gravity pull, it moves in circular track. Okay, so there is this delicate balance between this velocity, which we call tangential velocity. Okay, tangential velocity, which moves the Earth in the forward direction, and this gravitational force, which keeps the object or the Earth in circular track or circular path. So if one of these two were absent, then you can imagine what would happen. So if there were no gravitational force, then Earth would just move in a straight path. Okay, so it won't be in the circular track around the sun. And if there were no tangential velocity, imagine that this v is not present, Earth stops to move for a second, then it will just collapse towards the sun. Okay, it will collide with the sun. So this delicate balance between gravitational force and tangential velocity keeps the Earth in circular path. So that's the beauty of nature. Okay, so we say that nature is beautiful, and this delicate balance is what the beauty is in this case. Okay, so we'll talk a little bit more about gravitational force. So what this gravitational force is. So gravitational force was first discovered by Newton. Gravitational force was discovered by Newton, and he found that this gravitational force exists between any two objects in the universe. Okay, so you can have Earth and Moon, or Earth and Sun. So any two objects attract each other with a force, which is the gravitational force. Okay, it's universal, it's everywhere. No matter how small or big an object is, it exerts gravitational force on another object. So Newton found that this gravitational force is directly proportional to the product of the two masses. Okay, let's say you have mass 1 and mass 2, denoted by m1 and m2, and they are at distance d from each other. So the gravitational force, or the force of attraction between these two objects, is directly proportional to their product of the masses. Okay, m1, m2. What that means is, if somehow you double one of the masses, okay, so you have let's say this is m1, and now you double it, then what will happen to this force? If you double the mass, then the product will be doubled. Okay, now you have 2 m1 and you have m2, so the product of these two masses would be 2 m1 m2. Initially you have the product to be m1 times m2. Okay, now you have product is twice that. Then Newton found that now the force would also be double, okay, because force depends on this product. Doubling this doubles the force. Okay, if you somehow double both the masses, let's say you double this one, you make it 2 m1, and you also double this one, okay, keeping the same distance. Okay, we are not changing the distance. D is same. Here also D is same. Now what's the product here? Product is 2 times 2 is 4 m1 m2. So when you quadruple the product, you quadruple the force. Now here this force would be 4 times this force. Okay, here the force between these two objects would be 2 times this force. So that's what Newton found. You have this question, first question on worksheet 10. So for masses m1 and m2, let's say the force is F when the distance is d apart. Now if you double one of the masses to 2m, keeping the other one same, so how will that change the force? Okay, so you have to write in terms of F. So the first one would be, if you double the product, then the force would be doubled. So if initial force is F, then the force would be 2F after you double the product. Same thing with the second one also. If you double the second mass, keeping the first mass same, that means you are doubling the product. That means that doubles the force. Okay. So how about the third one? So how would that change the force? So what happens to the product when you double both the masses? You quadruple, yeah. So the force would be quadrupled. Okay, so the force would be 4F. So you write 4F for the third one, and then for fourth one, you double one first mass and triple the second mass, and see what happens to the product. So the product will be 6 times the initial product. So that will increase the force by 6 times. Okay. So that's what Newton found. And Newton also found that this force is inversely proportional to square of distance between the two masses. Okay, so you have mass m1 and m2, and the distance between the masses is d. When the distance is d, let's say the force is F between the two masses, and if you somehow double the distance, okay, keeping the masses same, so m1 m2, but now the distance is 2d. We know that if you move the objects away, then the force would decrease, okay, but decrease by how much? So that would be given by this inverse square rule. So according to this rule, if you double the distance, because there is a square here and it's inverse, so the force would be 1/4 that of this force. Okay, so this would be F over 4. Sorry, this is the force. So the force would be decreased by 1/4. Likewise, if you reduce the distance by 1/2, let's say your distance is d over 2, then we know that the force would be increased when you bring the masses closer. They will have more force, but by how much? That's given by this. Okay, so because you have square here, so you need to square that too. So the force would be 4 times, okay, 4 times this force. So this is called inverse square law. So in Newton's second law, we talked about this acceleration is inversely proportional to mass. This is just inverse law. Okay, so there is difference between inverse square and inverse law. In inverse law, if you double this thing, it will reduce this thing to 1/2. If you triple this, it will reduce this to 1/3. Or if you reduce this to 1/2, then this would be doubled. Okay, if you reduce this to 1/3, this would be increased by 9 folds. But here, because there is a square, so in case of inverse square, if you double the distance, then the force would be 1/4. If you triple the distance, force would be 1/9. Okay, not 1/3, but 1/9 because of this inverse square. Okay, if you decrease the distance by 1/2, then force would be increased by 4 times. Okay, quadrupled. If you decrease the distance by 1/3, then the force would be 9 times. Okay, so that's inverse square. So let's look at second question. So for distance d, force is F. Now you keep the mass same. Okay, we don't change the mass. Double the distance. So how will that affect the force? So force would be reduced. It would be reduced by 1/4. So 1/4 F. So when the distance is tripled, what happens to the force? So what would be the force for 3D? F over 4. Why is it F over 4? No, second one, sorry. When you triple the distance. Yes, F over 9. So distance would be, force would be 1/9, reduced to 1/9. How about the last one, d over 4? If you reduce the distance to 1/4, the distance, how will that change the force? 8, or you need to square that, right? So 4 squared will be 16, right? So 16 F. So this means you have to square that, and 1/, means it's just reciprocal of what you have. So if it is d over 4, then 4 would go on the top, so it would be 16 times. Okay, so Newton found these two laws. So he found force is proportional to m1 m2, product of the masses, and then force is inversely proportional to 1/d squared, and then he combined these two rules or laws in a single form. So F is proportional to m1 over m2 and then d squared, and then this is the proportional sign. So he converted this proportional sign into equal sign. Okay, so you can do that in math. In math, if you have a proportional sign, you can convert that to equal sign by inserting some kind of a constant. Okay, so you need to put a constant here, and he used this constant called g, which is called universal gravitational constant. Okay, and then he wrote this formula m1 m2 over d squared, and the value of this g is 6.67 times 10 to negative 11 Newton meters squared per kilogram squared. Okay, and it's always same everywhere in the universe. No matter where you go in the universe, whether it's on Mars or on Jupiter or on some other galaxy, its value is always same. Okay, unlike G is not constant. Okay, it depends on planet to planet. For example, the value of G on the surface of the Earth is 9.8, but if you go to Mount Everest, it would be less than that. Okay, it may be 9 or 8 or something like that. If you go to Moon, then on the surface of the Moon, G is only 1/6 that of the G on the surface of the Earth. Okay, so G is not constant, small g, but this capital G is always constant. So this formula gives us force, gives us the force between any two objects, in the universe. Okay. So let's look at number 3. Any two objects means any two objects. Okay, it could be living thing or non-living thing, or big or small, or any kind of objects. So here it's asking you to find the gravitational force between you and the person next to you. Okay, consider that both of you weigh 65 kilogram and you are 1 meter apart from each other. So M1 is 65 kilogram and M2 is 65 kilogram. So we want to find how much force you exert or you pull on your person sitting next to and on your friend or person sitting next to you. So formula for that is G M1 M2 over D squared. So G is always constant, 6.67 times 10 to negative 11 Newton meters squared per kilogram squared. Okay, that's the constant G. Mass, your mass 65 kilogram. The mass of the person sitting next to you is 65 kilogram, and then the distance is 1 meter squared. So do not forget to square this denominator. Okay, people often forget to square denominator and they get wrong answer. So it's very important to square the bottom of that expression. So do the calculation. Let's see if I have. Does anyone need the worksheet? So I don't have answer, so you guys can do the calculation and give me a number. It should be a very small number. So the force you exert on the person next to you would be very, very small. That's why you don't feel the force. So when the mass is small, the force is also small. Okay, so that's the force. It's just very, very small force. Okay, 10 to negative 7 means like you divide this 2.82 over 7 zeros after 1. 1, 2, 3, 4, 7. Which should be 0.1, 2, 3, 4, 5, 6. Something like that. Okay. Small force, very, very small force. That's why you don't feel any force. Now, let's look at number 4. So it's asking you to find the gravitational force between the sun and the earth. And the sun and the earth is distance between the sun and the earth is 1.5 times 10 to 11 meters, and the masses are also given. So you just need to use the formula. So G, mass of sun, mass of earth, and distance between sun and earth squared. 6.67 times 10 to negative 11 Newton meters squared per kilogram squared. Mass of sun 1.989 times 10 to 30th kilogram. Mass of the earth is 5.972 times 10 to 24th kilogram, and distance is 1.5 times 10 to 11 meter squared. And let's find that out. It should be a very big number, because sun keeps earth in circular orbit with that force. Okay. Okay, so that's the force. It's a very, very large force. And if you also want to write the direction, direction is always towards the center of the sun. We can just say towards the center of the sun. If you talk about sun from sun's perspective, the force will be towards the center of the sun. But if you think about earth, earth is also applying the same force. Okay, it's not just sun exerting the force on the moon, on the earth. It's also the same force that earth exerts on the sun. From Newton's third law, sun pulls earth. Okay, so this is the pull of sun on the earth with that much force, and earth also pulls sun with the same force. So these two forces are equal and opposite. Opposite means different in the direction. So this is the direction of pull of earth on sun, and this is the direction of pull of sun on earth. Okay, so there is mutual attraction. So instead of writing, because they are same, so instead of writing both forces, okay, this is force of sun on earth, and this is the force of earth on sun. So instead of writing that, we can just write F. If you write F, that means it's both force of earth on sun and force of sun on earth, because it's equal. Okay, so let's look at number 5. Calculate the gravitational force between the earth of mass 5.97 times 10 to 24th kilogram and 1 kilogram object on its surface. It's just using the formula, so there's nothing complicated here. So you have earth, and there is an object on its surface. Okay, so this is, let's say, mass of the object, and the mass of the earth is centered at its center, concentrated at its center. So this is mass of the earth, and the distance between this object and earth is this distance. Okay, distance is always measured from center to center. If you have two objects, then you measure the distance always from this center to that center. So here this is the center of the earth and that's the center of the object, and because the radius of the earth is much bigger than the radius of this object, so we can just neglect the object's radius. Okay, we can just consider this distance to be the radius of the earth. So let's call that radius of the earth RE. So gravitational force between the object and the earth is G, mass of the object, mass of the earth, distance between earth and object squared. So 6.67 times 10 to 11 Newton meters squared per kilogram squared. Mass of earth 5.97 times 10 to 11, sorry, not 11, time to 24th, 10 to 24th kilogram. That's the mass of the earth. Okay, I should have written mass of the object first, and the mass of the object is 1 kilogram, and distance is this distance, which is the radius of the earth. Radius of the earth is 6.37 times 10 to 6 meters, and then don't forget the square, and then see what you get. That should come out to be 9.8 Newton, more or less. And then it's asking to find the weight of the object. So weight, by definition, we know the formula for weight. Weight is m times g. Okay, so m, mass of the object, is 1 kilogram. G is 9.8 meters per second squared. Okay, that gives us 9.8 Newton. That's the weight. That's the gravity of earth on the object. So let's look at number 6. Same kind of question. Now this time it's asking you to find the gravitational force between the earth and a 65 kilogram person on the surface of the earth. Okay, so that's the earth and you have 65 kilogram person. So mass of the person is 65 kilogram. Distance between the person and the center of the earth is the radius of the earth, which is 6.37 times 10 to 6 meters. So gravitational force is 6.67 times 10 to negative 11. Okay, I will not write the unit. Mass of the person 65 kilogram. Mass of the earth 5.97 times 10 to 24th, and then the distance between the person and the earth center 6.37 times 10 to 6 meter squared. So that should give you 638 Newton. How do I know that? So let me do the second one first and then I will tell you how I know that. So W, it's also asking for the weight of the person. Weight is m times g. M is 65 kilogram. G is 9.8 meters per second squared. If you do that calculation, you get 638. Okay. What we see here is the weight of the person and the gravitational force of the person, of the earth on the person, are same. You see here also, this is the weight of the object and this is the gravitational pull of the earth on the object. They are same. That answers number 7. Okay. So, what can you say about the gravitational force between the earth and an object on its surface and the weight of the object? So, the weight is indeed the gravitational force between the earth and the object on its surface. Okay. So, that is what you see here. The weight is actually the gravitational force. So, that means if weight and gravitational force are same, that means these two expressions must also be same. Okay. So, force is g, mass of the first object, mass of second object, or in this case mass of first object and mass of the earth over radius of the earth. So, this is the force, gravitational force of earth on an object on its surface. Okay. That is the gravitational force. This is the mass of the object. This is m1. And because we just came to conclusion that this is also the weight. Okay. That is also the weight. Weight is also gravitational force. That means this expression must be equal to that expression. So, we can write mg, because these two represent the same thing. So, mg must be equal to, here we are talking about m1. Let us write m1 here. So, m1, let us just rewrite. So, m1g is equal to g m1 me over re squared. Okay. So, weight is gravitational force. So, we can cancel m1 and m1, then what we get, g is equal to g me over re squared. Okay. So, this is constant, the gravity constant or gravitational constant, and mass of the earth, they are both constant. Okay. That does not change, that do not change. So, that means we can write this as g depends on the radius of the earth. Okay. G is inversely proportional to distance from the center of the earth. So, acceleration due to gravity is inversely proportional to the square of distance from the center of the earth. So, what is the meaning of that? So, the meaning is g, the value of g varies from place to place. Okay. So, on or at sea level, its value is 9.8 meters per second squared, but on top of a mountain Should it be less than that or greater than that? If the value of g is 9.8 meters per second squared on the surface of the earth or at sea level, okay, here, then on top of a mountain here, should g be greater than 9.8 or less than 9.8? Less, yeah, because this is inversely proportional. Inversely means greater the value of r, smaller the value of g. Okay, when this goes up, this goes down. That's inverse. So depending on how big the mountain is, you'll have less value of g compared to the value on the surface. Okay. Now we can use this concept to do lots of calculations. One particularly interesting calculation we can do here is about the satellite revolving around the Earth. Okay, so let's consider we have a satellite, some kind of artificial satellite revolving around the Earth. So nowadays there are like thousands of satellites orbiting around the Earth, man-made satellites. Okay, so that's the satellite. Now this satellite, it has again two components. One is it moves in the forward direction with some velocity, with some tangential velocity, and because of the pull of the Earth, this remains in the Earth's orbit. Okay, so there is balance between this velocity, tangential velocity, and this gravitational attraction of the Earth. That keeps the satellite in this circular orbit. Okay, this is circular orbit. So what keeps this satellite in circular motion? It's this gravitational force. Okay, F G, or yeah, let's call it Fg. So the gravitational pull keeps the satellite in a circular orbit. Okay. That means the centripetal force, we know for an object to be in a circular orbit, it needs centripetal force, which is provided by gravity force or gravitational force. Okay. So the centripetal force comes from gravitational force. So we know the expression for centripetal force. We learned in the previous lectures. Centripetal force is mv squared over r. In this case, what is the revolving object? What is the object that is in circular motion? It's the satellite, right? So that means here this mass is the mass of the satellite. Okay, don't be confused with the Earth. It's not the Earth that is revolving, it's the satellite. So ms, this is object in circular motion. Okay, and it is provided by gravity force. So gravity force is pull between Earth and the satellite. So g, mass of satellite, ms, and mass of Earth, and distance. What's the distance between the Earth and the satellite? So the satellite is here. This is the surface of the Earth. Okay. So from the center to the surface of the Earth is the radius of the Earth. So this is the radius of the Earth, and from the surface of the Earth to the satellite is the height of the satellite. Okay, let's call that h. So what's the distance between the center of the Earth and the satellite? It's r plus h, right? Radius of the Earth plus height of the satellite from the surface. This is the distance. So we know force is g m1 m2 over d squared. So g, this is m1, that's m2, and this is distance squared. Okay. Here also it's not just r. Okay. So satellite is rotating about the center of the Earth. That means this distance should be same as that. So this distance would be the radius of the circular orbit. Okay, not just r. R would be when the satellite is very, very close to the surface, but that's not the case. Satellite is at certain height. So here we need to write r e plus h, not just r e. Okay, let me just write it more clearly here, r e plus h. So on question 8, it's asking to rearrange this formula or this expression and derive an expression for the speed of the satellite. So you want to write this expression in terms of v. Okay, v on left side and everything else on right side. So why don't you guys try that? So how can you simplify this? Whenever you have common terms, you can always cancel the common terms on the left and right. So what are the common terms here? This is common, right? ms and ms. So you can cancel that. And then we have re plus h squared, and here re plus h. So you can cancel one of the re plus h here, and this re h. So what is left here? So here you have v squared left, everything else is cancelled. On the right you have what is left, so gme over re plus h. So what is v then? V would be gme over re plus h square root. Okay, we have square here. To get rid of square, I am taking square root on both sides. So that gives us the speed of a satellite around the Earth. So that's what we want to find on number 9. So determine the speed of a satellite that is 150 kilometers above the surface of the Earth. So you have a satellite which is 150 kilometers from the surface, and from the center it would be 150 kilometers plus the radius of the Earth. Okay. So v is what we want to find. So g is 6.67 times 10 to the negative 11. I will not write the unit. Mass of the Earth, me is mass of the Earth, which is, we already used that. So 5.97 times 10 to the 24th kilogram. Radius of the Earth, we already used that. So 6.39 times 10 to 6 meters, plus height of the satellite from the surface is 150 kilometers. So here we are expressing this in meters, so I cannot write here kilometer, so I need to write this in meters. So kilometer to meter is 10 to 3 meter. Okay, so find that. Does anyone have answer for that? Okay, you can find that out. Okay, so next we consider that this satellite moves in a constant speed, okay, at a constant speed. This velocity or speed doesn't change, it remains same. You guys are still calculating. Okay, does anyone have answer?
I got 2.36 times 10 to the 34th power.
10 to what?
34th power?
34th? That is really, really high. Did you take the square root?
No, that's what I must have.
I got 7,768.
7,768. That seems reasonable. Okay. So that's about 7.8 kilometers per second. Okay. So you can double check the answer. Okay. I think seems like that's the right answer, but I'm not 100% sure what the right answer is. You can figure that out. So we assume that this is a constant motion. So for a constant motion, how do we define speed for a constant motion? Speed is distance traveled over time taken to travel the distance. Over time to travel that distance. Okay. So in one complete revolution, how much distance the satellite travels for one complete rotation? It's the circumference, right? CIRC, circumference. So, and that would be time period. So the time it takes to make one complete revolution is time period. So for one time period, it travels one circumference. So if I want to find the time period of a satellite, time period means how much time it takes to start from one point and then back again to the same point. Okay, so that would be given by rearranging that formula. So that would be circumference over speed. Circumference is 2 pi distance. Okay, r is the radius. Radius is center to satellite. Satellite is here. So that is distance from center to the satellite is radius of the Earth plus the height of the satellite over v. Okay, so let's find that. So 2 pi radius of the Earth is 6.39 times 10 to 6 meters. Height of the satellite is 1.5 times 10 to 5. 150 is 1.5 times 10 to 5 meters. And then v is whatever you get from here. So that's 7768 meters per second. Okay, so that gives you the time period for one revolution of the satellite. You can find also in minutes if you want, in hour. Okay. Okay. So please complete this and submit it on great scope. If you have any question, please let me know. We'll continue this in the next lecture. By the way, some of you are having trouble with expert TA homework 6 or homework 7, I don't remember. I may reset that again so you guys can do it again, or maybe we can, in the next class I will show you the problems that you are having trouble with. Okay, so don't worry about the problems if you didn't get it correct.